Last video. Let us be thorough, but let us be swift. Today we are going to talk about curvature of a parameterized curve, and we're going to talk about arc length of a parameterized curve. So let's go ahead and get started. Curvature. So for a vector valued function, curvature is a scalar. It's a real number that measures how quickly your object is turning. If the curvature is large, then your object is turning quite quickly. If the curvature is small, then your object is turning slowly. And if your curvature is exactly 0, then your object is not curving at all, and it's moving along a straight line. There are a couple of different formulas for curvature, and which one you generally use depends on what other quantities you might be asked for in the same problem. If you are given a vector valued function r of t and you're only looking for the curvature, then generally speaking, the most convenient formula is the following. You can take r prime of t, the velocity vector, cross it with r double prime of t, your acceleration vector, and calculate the length of that cross product. And then divide that quantity by r prime of t quantity cubed. This is equal to the curvature, which is usually called k, or Greek letter kappa, but I am incapable of drawing a kappa, which doesn't just look like a regular k. This is the curvature at any given time t. If you want the curvature at a specific time, you can then plug in that t value, but as always, make sure that you're plugging in that t value after all the derivatives have been calculated. Now notice that this formula can only be applied to a three-dimensional vector valued function. Because the cross product is only possible when your vectors are in three-dimensional space. Now this is most useful if you're calculating the curvature only. But there is another formula that's really convenient to use if you're working in a problem that asks you not just to calculate the curvature, but also to calculate that unit tangent, unit normal, and unit binormal vector that we studied in the previous video. So here's an alternative formula which bypasses the cross product at the cost of having to calculate a slightly different quantity. The curvature at time t can also be found by taking the unit tangent vector, calculating its derivative, taking its length, and then dividing that by the speed of the parameterized curve, r prime of t. Once again, only when all your derivatives have been calculated is it safe to plug in t equals whatever value you have been given. This is most useful in the case where you're calculating the curvature and the t and b vectors in the same problem, because when you're going to calculate the unit tangent vector, you need to get this quantity r prime anyway. When you're going to calculate the unit normal vector, you're going to need to get this quantity t prime anyway. And for that reason, I would say that this is most useful if also calculating the t and b vectors. The unit tangent, unit normal, and unit binormal vectors. For example, In this problem, I'm being asked to calculate the curvature of the parameterized circle r of cosine t r times sine t 0. Now, notice that this curve is functionally two-dimensional because only the x and y are changing and the z is constant at 0. But remember that curvature is something that can only be calculated using a three-dimensional representation of that movement, because we do have to calculate the cross product. And cross product is only something that can be done with three-dimensional vector-valued functions. So let's determine the curvature of a circle of radius r. Now the first thing that we need to do is we need to calculate, well, I'm going to go ahead and use the formula r prime of t cross r double prime of t divided by r of t, the length of all those vectors with the bottom one cubed. I'm going to use this because this particular question only asks me to calculate the curvature and it doesn't ask for any other quantities. So I'm going to need to find these derivatives, r prime and r double prime. So r prime, if I take the derivative one component at a time, we get negative r sine t, we get r cos t, and of course 0 remains 0. While we're at it, here's r double prime, negative r cos t, and then negative r sine t, once again 0. Now if the problem had anywhere given me a particular t value, this is the moment when I would plug it in, because this is the moment where all the derivatives that we need to calculate have been calculated. However, this question doesn't give me a particular value of t, so we need to find the curvature function, k of t, the curvature at any given time, and so I have to leave these two vectors as functions with an unknown t value. With that in mind, let's go ahead and let's calculate the cross product. Even though these vectors have variables in them, the cross product can be calculated exactly the same way, as a 3 by 3 matrix determinant. Negative r sine t gives here r cos t 0, and then negative r cos, negative r sine on 0. This is your first introduction, I think, to a matrix that has functions in it. Okay, so let's calculate the product that we would need for the x component. R cosine t times 0, r sine t times 0, both of those products are 0. Similarly for j. For the j component, for the second number, negative r sine t would be multiplied by 0, and so would the negative r cos t. It's only the final component that starts to get interesting. For the final component, looking at the products in the first two columns, we have negative r sine times negative r sine. The two minus signs cancel, giving me positive r times r, sine times sine. Adding r times r, cos times cos. Now, do you remember when we said that Pythagorean identity was going to be our best friend in this section? Well, here we are again. We have a sine squared plus cosine squared, both being multiplied by the same constant, r squared. So that simplifies, by the Pythagorean identity, simply to r squared. And this is true for any and all values of t. So let's go ahead and let's get the length of this vector, and that will be equal to our numerator. But the length of a vector with only one non-zero component is just equal to the absolute value of that component. The length of that vector is just r squared. Now let's go ahead and finish the denominator, the length of r prime. So if I go ahead and calculate the length of the vector where we had negative r sine t, r cos t and 0, then I would be calculating the square root of the first component squared, r squared sine t, plus the second component squared, r squared cos t. Both sine and cosine are squared as well, and then 0 squared doesn't do anything. So this is equal to the square root of r squared, which simplifies to r. And I am going to go ahead and make the assumption that r is positive. If r was negative, then it would be absolute value of r. But I just forgot to write it really. I did have in mind that this r was supposed to be positive. Having found all of these pieces, let's go ahead and put them together in the formula. The curvature at any given time is equal to the length of the cross product, which we found to be r squared, divided by the cubed length of the velocity vector. Now the length of the velocity vector was r, so the cubed length has got to be r cubed. And if we simplify that, we get 1 over r. So the curvature of moving in a circle at any given time is inversely proportional to the radius of the circle, which matches our understanding from real life. As a circle gets larger and larger and larger, the curve of that circle becomes less and less apparent, until we get to the point where we're on a really, really big circle, such as a planet, and the circle is so big and has such a large radius that it almost seems like the planet isn't curving at all. It almost seems like the planet is flat and you're traveling along a straight line as you go around the planet. Now, just for a point of comparison, let's consider the following exercise. We have a vector valued function t squared 2 over 3t cubed t. And we need to find not only the curvature, but also the t and b vectors, unit tangent, unit normal, and unit binormal vectors at a specific point. Now notice that the point 1, 2/3, 1 will be achieved when the t value is equal to 1 exactly. Oh good, Windows Defender didn't find any threats. So let's go ahead and find the curvature and the t and b vectors at this specific time. So in pursuit of these quantities, we're going to need to fill in the blanks of the following. If we want to find the unit tangent vector, we need to find the velocity vector and divide it by the speed. Once that's done, we need to find the unit normal vector, which involves taking the derivative of the unit tangent and dividing it by its length. Now, on that journey, we will have by then found the length of r prime and the length of t prime. So it seems like a good opportunity to calculate the curvature using the formula length of t prime divided by length of r prime. And then we can get the unit binormal vector by crossing the unit tangent and unit normal vectors. So the first thing that we need to do is get this velocity vector, r prime. R prime of t is equal to the derivative of t squared, the derivative of 2 over 3t cubed, which is 2t squared, and the derivative of t, which is just 1. Now let's record the length of this quantity. The square root of 2t quantity squared, which is 4t squared, 2t squared quantity squared, which causes that 2 to become a 4, and then 1. Now under normal circumstances, the square root of a sum of terms like this cannot be simplified. But in this special case, I think we can do some factoring. I think that this radicand, this quantity under the square root, is equivalent to 2t squared plus 1 quantity squared. We can check that by going backward. We have 2t squared squared, that's the 4t to the 4th power. We have 2 times the product 2t squared times 1, That's the 4t squared. And then we have 1 squared, which is the plus 1 in the back. So this can be simplified to 2t squared plus 1, which is really lucky. Now that we have found these quantities, we can put them into the formula for the unit tangent vector. Which is equal to the velocity divided by the speed. 2t over 2t squared plus 1, 2t squared over 2t squared plus 1, and 1 over 2t squared plus 1. Now tragically, we cannot yet plug in the given t value because all of our derivatives have not yet been calculated. It still remains for us to calculate the derivative of this unit tangent vector, capital T. So we're going to have to get some ugly quotient rule involved. So for the x component, for example, we have the denominator, the bottom, times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Same thing for the y component. For the y component, we need to use quotient rule to say that this is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And finally, for the last, we can use chain rule if we want to, or we can use quotient rule. Z I might think of as bottom times the derivative of the top minus top times the derivative of the bottom, just for symmetry in terms of calculations, all over the bottom squared. Now, at last, finally, all the derivatives have been calculated, and it's safe to plug in the given t value. So let's go ahead and plug in t equals 1. The length of r prime with t equals 1 is equal to this formula in blue with t equals 1. So that's 2 times 1 squared plus 1, that's 3. We can also get the unit tangent vector at this time, which was one of the quantities that the problem was looking for. That's 2 over 3, 2 over 3, 1 over 3. We're also going to need t prime. Now it looks like all these denominators are going to be 9, so let's just think about what the numerators would be. So if t is equal to 1, we get 3 times 2, that's 6, minus 8, so that's minus 2. When t is equal to 1 here, we get 3 times 4, that's 12. Take away 8, so that's 4. And when t is equal to 1 here, this numerator is just minus 4. So we get negative 2, positive 4, negative 4. Each divided by 9. Now let's get the length of this guy, which is equal to the square root of the first component squared, 4 over 81, then 16 over 81, then another 16 over 81. So these numerators combine to 36 over 81, and that's equal to 6 over 9, or 2/3. So if I go through and divide each one of these components by t prime, I'll get the unit normal vector. So we get negative 2 over 9 divided by 2 over 3. So I'll multiply it by the reciprocal. I'll multiply this by the reciprocal. And I'll multiply the last component by the reciprocal. And so our unit normal vector is equal to negative 1 over 3, 2 over 3, and negative 2 over 3. As of this moment, we actually also have all the components that we need to get the curvature. We have the length of r prime and the length of t prime. The curvature is just equal to the length of t prime divided by the length of r prime. So that's 2/3 for the length of t prime divided by 3 for the length of r prime. And finally, we're almost there, finally, we can get the unit binormal vector. So here's the curvature. For the unit binormal vector, we can cross tangent with normal. So the curvature is equal to 2 over 9 at time t equals 1. So I just went upstairs to recover the components of t and n. We have 2, 2, 1 all over 3 for t, negative 1, 2, negative 2 all over 3 for n. So let's go ahead and calculate the x component. 2 times minus 2, negative 4 over 9, minus 2 times 1 over 9. For the x component, we have 2 times minus 2, which is negative 4 over 9. Take away negative 1 times 1, so add 1 over 9. And then for the y component, 2 times 2, 4 over 9. Take away negative 2 over 9. So we get negative 6 over 9, which is negative 2/3. We get negative 3 over 9, which is negative 1/3, and then make the sign opposite. We get 6 over 9, which is positive 2/3. And there is our unit binormal, which is the last component that we needed for these calculations. Our last topic is going to be arc length. In my opinion, a little bit easier than what we did in the curvature section. The idea is this. So suppose that an object is moving along a track, which is given by the output of the vector valued function where we have cos, sine, t. So here is our friend the helix. Someone says find the distance between the object's starting position and its final position, starting from t equals 0 and ending at t equals 2 pi. Is this distance from start to finish the same thing as the distance traveled by the object moving along this track? Now, we can answer the second question immediately, I think. The object starts here at the positive x-axis, loops around as if on a spiral staircase. When the time is 2 pi, the object is back hovering above the positive x-axis, but this time the z value has grown to 2 pi units. So the distance between the object's initial and final position is measured by this straight orange line segment. Distance between the output of the function at 2 pi, the final time, and the output at 0, the initial time. Visually, we can see that this is going to be significantly smaller than the actual distance traveled by the object, because the object didn't move in a straight line directly from one point to the other. It took a less efficient route to get to the final position. The distance traveled is probably going to be significantly larger than the distance from the starting position and the final position. If I calculate r of 2 pi, if I calculate the object's final position, then 2 pi gives me 1 from cos, nothing from sine, 2 pi from t. If I plug in 0, I likewise get 1 from cos, then 0 from t. So if I calculate the distance between these two positions using the 3D distance formula, I get 1 minus 1 squared, 0 minus 0 squared, 2 pi minus 0 squared, which simplifies to 2 pi units. Basically, just the difference in height between one point and the other, not including all this x and y movement that happened in the process of getting from one point to the other. Now, in formal terms, if you want the distance between an object's initial position and its final position, this quantity is called the displacement. The displacement of an object is the difference between where it was at the beginning of its motion and where it was at the end of its motion. Displacement does not care about how the object moved between the initial and final times. It only cares about the difference between what happened at the start and what happened at the end. In general, in almost all cases, the displacement is not equal to the actual total distance traveled by the object. They are only equal when the object was moving consistently forward in a straight line. If the object moved directly from point A to point B, then the distance traveled by the object and the displacement are equal. But if the object did anything else, if it stopped to smell the roses along the way, then the distance traveled by the object is going to be significantly larger than the displacement. So the question is, if the distance traveled by the object is not equal to the distance between the initial position and the final position, how does one actually calculate the distance traveled by the object? How does one calculate the length of this blue curve that captures the entire journey taken by the object as it moved? Now, as usual, we're going to take our inspiration from Calculus 2. In Calculus 2, we had a one-dimensional position function, and if we wanted to calculate the displacement, if we wanted to calculate the difference between the initial position and the final position, we could do that by integrating from the initial time to the final time the velocity of the object. However, if we wanted the distance traveled, what we would do is integrate from beginning to end the speed of the object, velocity with an absolute value. Unfortunately for us, the formula and the idea is exactly the same here. If you want to find the distance traveled by an object, integrate from the initial time to the final time the object's speed, the magnitude of the velocity vector. In case your vector-valued function doesn't represent a position of an object, if you're just thinking about that function in abstract mathematical terms, we still have a name for this quantity, where you integrate from A to B, r prime of t length. This quantity is called arc length. Arc length from t equals a to t equals b, because it is literally the length of an arc, the length of the piece of the curve between t equals a, the initial time, and t equals b, the final time. So you may hear this term used as well, arc length. So to see an exercise, let's go ahead and go back to that helix example, and let's calculate the actual distance traveled by the object between an initial time of t equals 0 and a final time of t equals 2 pi. In order to do that, the first thing that we need to do is get the object's speed. So let's go ahead and calculate r prime. Component-wise, this is negative sine, positive cos, and 1, which means that the length of that is now equal to the square root of sine squared plus cos squared plus 1, which is simply equal to the square root of 2. As a result, the distance traveled, not equal to the displacement, is equal to the integral from the initial time to the final time, the integral of the speed. So, integral of a constant is that constant times the variable. And if I plug in those limits of integration, the distance traveled is root 2 times 2 pi. About 50% larger than the displacement, the distance between the object's initial position and the object's final position. Alright, that concludes the final video of the course. We talked about how to calculate curvature, which is a measure of how much an object is turning. We talked about curvature as calculated when that's the only quantity that you need in the problem, and then we introduced an alternative formula for curvature that is most convenient when you are also being asked to find the unit tangent, unit normal, and unit binormal vectors. Then we introduced arc length. Arc length is a general abstract math term. In the case that your vector valued function represents position, arc length is equivalent to the total distance traveled by the object. And that can be calculated just as in Calculus 2 by taking the integral of the object's speed, magnitude of r prime, from the initial to the final time. Alrighty folks, good luck with all your exams.